All right, this lesson is on solving exponential and logarithmic equations. We're just going to solve a bunch of equations here so that you'll know what to do. The first one that we're going to do is we're going to solve an exponential equation. Let's say we have 2 to the x equals 90. Now, the exponent is x. That's the variable I'm trying to solve for. And when we have a situation like this, when we're trying to solve for a variable that's actually in the exponent, what I'm going to do is take the log of both sides of the equation. Right? You learn that you can do whatever you want to one side of an equation as long as you balance it out by doing it to the other side. So I'm going to take the log of both sides. Since we want to use our calculator, we will use a log base 10. We'll use a common log so that our calculator can help us out. So log of both sides, like that. Now, using our property number 7, which was in the previous lesson, property number 7 was the one that said if I have an exponent inside the logarithm, that exponent can go out in front. And so that's now x log 2 equals log 90. This will now allow me to solve for x. If I divide by the log of 2, I get log 90 divided by the log of 2. That is the exact answer. Usually they ask for a decimal approximation. I'll round to 2 decimal places here. The log of 90 divided by the log of 2 using my calculator is approximately 6.49. And so I solved the equation for x. Here's another one. 10 to the x equals 4. So what I'm going to do here is take the log of both sides again, common log. There we go. Take the log of both sides. Use one of my properties of logarithms to drop the exponent into the front of the logarithm. This now gives me x times log 10 equals log 4. Divide both sides by the log of 10. And the common log of 10, by the way, is just 1. This is equal to 1 here. And so this is really just log 4. Let me use my calculator to get an approximation. The log of 4 is about 0.60 approximately. Okay, so to solve these exponential equations, what we're doing is taking the log of both sides. A couple more examples of this. Let's see, solve actually on all of these. E to the 3x equals 72. Now, to solve this equation for x, since it involves an e as a base, instead of taking the common log of both sides, I'm going to take the natural log of both sides. So I'm taking the natural log of both sides of the equation. Because there's an e in this, it will make the calculations a little simpler. Just like in the last examples, after I take the log of both sides, I can take the exponent and drop it into the front, which gives me 3x natural log e equals natural log 72. Now, the natural log of e, if you don't remember, let me do some work up here. The natural log of e is 1. And that is because the base for a natural log is e. So e to the first power is e. Okay, good thing to remember that this is equal to 1. So that gives me 3x equals natural log 72. Divide by 3. the natural log of 72 over 3 is my answer. I want a decimal approximation to that, so I can use my calculator. Natural log 72 divide by 3. You should have about 1.43 as our answer. Let's try one more. Let's try e to the 2t minus 1 equals 5. Okay, once again, to solve the equation, in this case for t, I'm going to take the natural log of both sides. Just like that. I'm going to drop the exponent into the front, so this is going to go to the front. And so I have 2t minus 1 in parentheses, natural log e equals natural log 5. Remembering that the natural log of e is 1, this will disappear on us. It's just a 1. So this becomes 2t minus 1 equals natural log 5. I can move the 1 over to the other side. 1 plus natural log 5. Divide by 2. And t is 1 plus the natural log of 5, all divided by 2. If I type that in my calculator, I can get an approximation. About 1.30 is our answer. Okay, and that's how we solve exponential equations. We take the log or the natural log of both sides. Now for some logarithmic equations. Solve. The log base 2 of x minus 5 equals 3. Now, with this logarithmic equation, what I'm going to do is I'm going to put it into exponent form. That's all I need to really do to solve it. And to put it in exponent form, remember we start here. That's our base. And we're going to rewrite this as 2 to the third power. 2 to the third power equals x minus 5. Okay? Let's put it up here. Write in exponent form. And this way I can now solve for x. So this is 8 equals x minus 5. X is 13. X equals 13. Log base 2 of x plus log base 2 of x minus 7 equals 3. Okay, now before I can put this one into exponent form, I have to combine the two logs into a single log. These two logarithms, they're added together, and so if we use one of our properties of logarithms, the addition can be turned into multiplication. This is the log of x times x minus 7 equals 3. Okay, I believe that was our property 5 in the last lesson. The addition can be turned into multiplication. Now that it's one single logarithm, I then put it in exponent form. Exponent form. And this is very similar to the last one now. 2 to the third power will equal this. 2 to the third equals x squared minus 7x. That's a quadratic equation, so I move this 8 to the other side, like that. I can then solve this equation by factoring. It factors to minus 8 and plus 1. And so we get two possible solutions. We get 8 or negative 1. Now, you cannot plug in negative numbers into a logarithm. The log of a negative number is undefined. So if you were to try to take, for instance, negative 1 here and plug it into the original equation there, you'd have to calculate the log of negative 1, which doesn't exist. So the only number that's going to work here is 8. I have to rule this one out. So our solution is 8. Let's do another example similar to that. Solve log x plus log x minus 21 equals 2. I need to combine the two logs into a single log first. So the addition here becomes multiplication. This is the log of x times x minus 21 equals 2. I've written it as a single log. Write as a single log. Now that I have it as one logarithm, I'm going to put it in exponent form. Since there's no base, this must be a common log, which is base 10. So 10 squared must equal this. 10 squared equals x squared minus 21x. There's my equation in exponent form. 10 squared is 100. And so this is a quadratic. I'm going to move the 100 to the right side. I can then solve this equation by factoring. It factors to minus 25 x plus 4. And so two possible solutions, x equals 25 or x equals negative 4. Now, just like in the last example, if I were to try to plug in negative 4 up here into the original equation, the log of negative 4, I can't do that. And so I have to rule this one out as an answer. My only solution that's going to work here is 25. X equals 25 is our solution. Log base 3 of 2x minus the log base 3 of 3x plus 15 equals negative 2. Okay, once again, I have to first combine the two logs into a single log. We have a property of logarithms that says the subtraction of two logs will turn into division. And so this is now the log of 2x divided by 3x plus 15. I wrote the two logs as a single log. Now I put it into exponent form, just like I've done with all the others. Exponent form now. 3 to the negative 2 should equal this whole thing in the parentheses. 3 to the negative 2 power equals 2x over 3x plus 15. 3 to the negative 2 is a 1/9. Probably the fastest way to solve this equation for x at this point would be to cross multiply. That's 18x equals 1 times 3x plus 15. Move the 3x to the other side. 15x equals 15. X equals 1. Now, if I plug x equals 1 into the original equation up here, as long as it doesn't give me the log of a negative number, it's going to be fine. It's going to work. And this one is going to work. It's our solution. So our solution is x equals 1. Okay, a couple more. Solve. Log base 2 of x plus 1 is equal to the log base 2 of 9. Now, what makes this one different from all the others is that I have a log on both sides, logarithm on both sides. And when that's the case, you can sort of just eliminate the two logarithms. The rule is this. If I have the log of a equaling the log of b, then a must equal b. In other words, if I have a log equaling a log, same base of course, these logarithms will just go away. and I'm left with x plus 1 equals 9. Very simple. X must be 8. And so I've solved for x. Here's another one. The log of x plus 1 minus the log of x equals the log of 7. Now I can't just cancel all the logarithms right now. I have to have it as a log equaling a log. So I first must combine these two logarithms into a single log. The subtraction will become division. The left side is the log of x plus 1 over the log of x. And the right side is the same, the log of 7. Now that I have a log equaling a log, I can use this property here. These logarithms, in a sense, sort of just go away. And I've got x plus 1 over x equals 7. To solve that equation for x, I'm going to put a 1 under the 7 and cross multiply. 7x equals x plus 1. Let me move this up here. 6x equals 1. Our solution here for this equation is 1/6. So we've got our answer 1/6. Okay, and that's basically how we solve our log equations. We did an example of each possible case. Let's now look at an application, one application. It's the compound continuous interest formula, and it's right here. P is the amount of dollars that you put into a bank account. It's earning an annual interest rate R, compounded continuously for T years. So this formula right here is for when you take a lump sum of money, you put it right into some sort of an account earning interest, you leave it there for a certain amount of time. How much money will it grow to? Let's look at our first example. How much money will be in an account at the end of 5 years? So T equals 5. If $1,000 is deposited, that's the original amount, or the principal amount is $1,000. 6% is our interest rate. As a decimal, that's 0.06. And compounding continuously means we're going to use this formula. So A equals, the principal amount is P, which is 1,000, times E to the R times T, which would be 0.06 times 5. That's 1,000 E to the 0.3. Now we're going to round our answer to the nearest penny. The first thing I have to calculate is E to the 0.3, then multiply by 1,000. The E button is usually above the natural log key. If you have a natural log key, you'll find E to the x up there. Times 1,000, and we have about $1,349, and rounding to the nearest penny, 86 cents. And so that's how much money we would have after 5 years compounded continuously. Let's look at another example. How long would it take for the $1,000 to double? So in this case, we've got P is 1,000. We know A. We want A to double. We want the principal amount to double to $2,000. The interest rate is still 6%, and the time is what we're looking for. How long will it take to double? So 2,000 equals 1,000. E to the 0.06 t is the equation, and we need to solve that equation for t. First thing I can do is divide both sides by 1,000, which gives me E to the 0.06 t just equals 2. Now we have solved equations like this earlier in the lesson. To solve this equation for t, I take the natural log of both sides. That will allow me to take this exponent and move it to the front. So I now have 0.06t natural log e equals natural log 2. The natural log of e is 1, and so it's gone. And so we end up with t is going to equal the natural log of 2 over 0.06. Type that in our calculator, and we get our answer. T is about 11.6 years, and so that's how long it would take for us to double our $1,000. And that is our lesson on solving exponential and log equations.